So what we're going to do, Justin, over the next couple of days is we're going to try and figure out how things move and how we can predict how they'll move. We're going to start out doing it graphically because graphically our eyes are good at spotting visual patterns. Remember the baby name thing that I showed you? Our eyes are good at spotting visual patterns, which is fine, but graphically takes a long time. So after a couple of lessons, what I'm going to try and then do, Jordan, is nudge you into the magic world of doing it with an equation, with algebra, with 3 lines, as opposed to a page of drawing. It's a better way to get, but we always start out graphically because it's a good way for us to visualize what's going on. But eventually we're going to leave the graphs behind. They're inefficient. Cool, but inefficient. So what we're looking at today, Spencer, are distance versus time graphs. Time will go on the x-axis because 99% of the time goes on the x-axis. Distance will be on the y-axis. So I made up some data. A person is walking along a straight line. You notice how I'm including some vector direction in there just so I don't have to deal with it. And they're being timed while their position from the starting point is recorded. The data is recorded in the following table. It says graph the data below. Okay, we're doing a science graph. What does every science graph have to have? Oh, title. So let's put here, how about distance versus time graph? I wanted to call my graph an ode to lateness. No, not a title like a novel, or no, just give it a basic title. What else does every science graph have to have? Before we even start plotting stuff. Scale, we're going to do that next, but even before I do that. Okay, label the axes. So I'm going to have distance, d in meters, and, get a little higher, I think I can. Time, t in seconds. Those to me, I mean, I can't call them no-brainers because, Thomas, you have to know to do them. But if on a test they say graph this, that's like, okay, get this, check, get this, check, get this, check. Okay, now go look at the data and start thinking. But I kind of do that almost absent-mindedly, like, oh, I just got to get it done. Okay. Now, yes, someone said scale. What do you want to do first? The x-axis scale, horizontal, or the y-axis scale, vertical? I don't care. Spencer, pick. Time, okay. What's the smallest time value in my chart? You know what? I'm going to start at 0. We almost always try and put time 0 on the graph. What's the biggest? So I need to fit from 0 to 9. How many squares how many hash, let's see. 1, 2, 3, 4, 5, oh heck. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 squares. You know what? Each big hash mark, why don't I let that be 1? So every square is a half. Is that okay? So I'm going to go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That uses up most of the graph. Alexa, we said the rule for a good scale was try and use up most of the graph paper. I would not have gone up by 1s. That would have had the 9 right there. You're only using 1/2 or less than 1/2 of your graph paper. You could have done better. Vertically, distance. Although my smallest value is 4, again, I like to try and fit 0 on the graph. What's my biggest value? 20. 1, 2, 3, 2, 4, 6, 8, 10, 12, 14. How can I fit 20 on here with 14 squares? I did this on purpose, by the way, to make you think. What if could I go 2, 4, no. You know what? I think each square is going to be 2. Let's see if this works. Count with me. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 20. That fits the 20, but I'm not going to label every square. It's going to get cluttered. What's each hash mark worth if each square is worth 2? So you know what? Let's go 4, 8, 12, 16, 20, 24, 28. Is that okay? There might have been other scales, but I always try and use 1s, 2s, 5s, and 10s. Like, yeah, you can go up by 3s or 7s or pick nice numbers if you can. So you ready? Let's graph. I've scrolled down. What's the first point? What's the time coordinate? Was it 4? You guys have it in front. I've scrolled down. What is it? Oh, 1 comma 4. Sorry. Okay, I can do that. I'll do these in black. 1 over, 4 up. What's the next one? 2, 6. 2, 6. You can tell these are fake points that I made up because right now they seem to be nice and right on lines. Usually you'll have like decimals and yuckiness, but that's okay. What's the next one? 3, 8. Oh, I'm spotting a pattern. Are you? I hope. Is the next one 410? Yeah. Woohoo! 512? How far do I go? 6, 14, 7, up to 9. Okay. So 6, 14, 7, 16, 8, that, 9, that. Again, I cooked the data. I just made up nice numbers. Usually in real life, you'll find there's some variation. Hey, we can draw a line of best fit. By the way, can you see what the y-intercept would be? Spot the pattern. Will it go through 0, 0? No. What will it go through? Okay, let's add that in. Lay down your ruler. Draw a nice line of best fit. I'll try and do it here. There's my graph. What we want to talk about today is what this shape tells me about how this person is moving, how fast they're moving, what direction they're moving, and whether they're moving at a constant speed or a changing speed. So let's answer some questions. What's the y-intercept of this graph? What, comma, what? Hang on, I got a latecomer. What's the y-intercept of this graph as a point? What, comma, what? 2 comma 0. Is 2 comma 0 correct? Ah, and that's a classic mistake. Kids do that all the time. They do y comma x. Okay, always x comma y, and you're saying the y-intercept is 0 comma 2. Now that's what it is as a point. What is the y-intercept as a meaning in English? Say what? At time 0, how high were we on the y-axis? 2. But what are we measuring on the y-axis? Distance. You know what? I think that's the initial position. This person started 2 meters from the start line. They already had been traveling for 2 meters when we started our stopwatch. So in English, we could say this is which one do you want? Well, usually I want the number if I ask you what's the y-intercept. But if I say, what does the y-intercept mean? This is what I'm getting at. What's the slope of this graph? How do I find slope? Slope is what over what? You know what? Let's write that. So what's our symbol for slope? What letter do we teach you in Math 10? M. Why M, by the way? Because not all math was done by English-speaking people. I think the M comes from a French word for mountain or steepness. Ah. You don't need to know that, but I'm a nerd and always, you know. So anyways, M, let's write down in our notes. Now, in your homework, you don't have to go all this detail, but I always go more detail in the notes, so when I'm studying, I know what the heck we did. M is rise over run. And I'd like to show you a classic mistake. So once you've written that, put your pencils down. Here's a classic mistake. I see far too many kids go, oh, the rise is 1, the run is 2. What they've done is they've counted squares. But is each square worth 1 necessarily? You have to look at your scale. So I would probably draw that little triangle somewhere on my graph, but how big a distance is that to there? Is that a 9? Ah! Okay, so now let's pick our pencils up and let's write slope is 2 over, and although this is 2 squares, how far is that on my scale? 1. Totally different slope. I see that all the time. In fact, on the Math 10 provincial exam, they love giving a question with a wonky scale and saying, hey, what's the slope? And they would have 1/2 as an answer to pick from. And in fact, if they're really mean, 1/2 would be answer A, the first one the kids see. And they're hoping the kids are silly enough to, that's great. Okay. Okay. Anyways, I'm going to nuke the red. I'll go back to blue. 2 over 1. Units. The 2 is the rise. What's on the y-axis? What units rise is y-axis? What units did I put on the y-axis? Read on the graph. Meters. Over. The run is the x-axis. By the way, I'm showing you a great trick right now so that you can cut down your memorizing. The run is the x-axis. What units are on the x-axis? T is the time. What units? Seconds. Hence my rant. Now here's my question. If I said to you, what does the slope mean? Look at the units. Meters per second. What is that a measure of? What does the slope mean? What have we been measuring in meters per second? What? Velocity. Kyle, in Physics 11 and in Physics 12, I'm going to give you a zillion graphs, and one of the classic questions is, tell me what the slope means. You can memorize every single graph, or do you see how I used the units to figure out what the slope had to be? That trick of taking the y units over the x units, 99% of the time by looking at the units, you'll figure out what the heck the slope means, and you don't need to memorize all 80 different graphs. So science 10, I know some of you are grade 12, but remember, science 10, they gave you all the stupid graphs. You have to remember, what's the slope of... What a waste of memorization. I can figure it out in 1 second by just looking at the units. Just looking at the units. C, what's the equation? Okay, who remembers, and I know we did this at the beginning of the year, last unit, which is why I snuck it in, but now again, what's the slope-intercept form template? What equals what plus what? Okay, let's write down y, let's change colors, Mr. Dueck, for this one. As my template, let's write down y equals mx plus b. We are almost never going to use the letter x and y. We're going to pick letters that make sense. So the y-axis, what variable did we stick on the y-axis? Justin, what variable did we stick on the y-axis? What variable did we stick on the y-axis? Read that to me, my friend. What would be a good letter to use for distance? What variable did we stick on the y-axis? What letter am I drawing a little circle around? Thank you, Captain Obvious. So we're going to write our equation as d equals, Justin, my friend, m was the slope. What did we just finish saying in part B the slope was? As a number. 2. Do you need to write 2 over 1? No. So 2. I'm not going to write x. Justin, what? I'm not going to help you this time. What variable did I use on the x-axis? Figuring it out now? Yeah, it was so obvious that it was tough. Yeah, I know. By the way, I saw you were zoned out somewhere. Totally picking on you. Sorry. Plus, b is the y-intercept. Hey, what did you say the y-intercept was? I think we did that in part A. One square, but... Right? Too hot, because, okay. Okay. If you wanted to, in English, you could say something like, and don't need to write this down, distance equals velocity times time plus initial position. Here's what it's saying. You want to know how far you've traveled? You need to know where you started from, initial position. And then the rest, if you're going at a constant speed, tell me how long you traveled and what your speed was, and that's the distance extra that you traveled. That doesn't seem, maybe that sounds profound, maybe it doesn't. You kind of do this when you're planning trips intuitively, but we've done it mathematically. And eventually, we're going to come up with an equation that contains this, but much shorter, much better, and more flexible. This is for a constant speed. Eventually, I want to deal with, hey, what if I'm speeding up or slowing down, because that's way more interesting. Turn the page. Here is the key idea. Here is the key idea. Thomas, can you read to me the key idea?
The slope of a displacement versus time graph is the velocity.
Lightning should flash. Thunder should roll. It's the key idea. Ta-da! The slope of a displacement versus time graph is the velocity. In fact, I'm going to go like this. Now, you can memorize that, or, Devin, I just showed you a clever way by looking at the units that you can derive that every time. Probably you'll memorize this particular graph because it shows up so often, and you'll get tired of having to do the derivation. I'll stick that in my brain for a while. But by the end of the year, you might have forgotten. Come final exam time, divide the units. Whenever they're talking about slope, Alexa, it's always the y units, rise, over the x units, run. And you can usually figure out what the heck the slope means. What if we have a changing velocity? Describe what's happening over each interval of the distance versus time graph below. So I've given you points A, B, C, D, and E. Lovely graph there. You ready? Can you tell me any times that you think we're traveling backwards? Now, what would backwards look like in terms of a slope? What did we say last day in terms of vectors? How are we going to show backward? Yeah? Shouldn't A and B be, oh, you know what? I keep forgetting to correct this graph. Candy for you, sir. You're right. This is going to be 20 high. This has been like, okay, you know what? First of all, let me do this. Pause the video for 1 second. I think there's another glitch on here too, if I recall this stupid graph. Let's see. That works. That's not a 50, really, is it? That is a, if you try reading across, that was supposed to be a 60. By the way, you see what happened? I started counting by ones instead of by, it happens to me too. Is the 40 right though? Yeah, the 40 looks right. Okay, back to my original question. How did we say we're going to show going backwards in terms of vector math? Do you remember? Huh? Okay, so if I say which sections are going backwards, what I'm saying is which slopes are negative. What's a negative slope look like? Downhill. Okay, so we're going to come to that in a second. Look up. What's traveling faster, this or this? Steeper. Okay, so in terms of speeds, steeper is faster, shallower is slower, downhill is backwards, downhill really fast, backwards really fast, backwards not so fast. What would this mean on a distance versus time graph? What would a horizontal line, what would section AB mean? First of all, what's the slope of that as a number? 0. What's the velocity of that as a number? 0. So not at a constant pace. If your velocity is 0, what are you really doing? Stopped. Okay, you can get all this information from the picture. So you ready? I wrote down here, describe what's happening in each interval over the distance versus time graph below. So let's use arrows and let's point right here first of all. Direction. First of all, are we traveling? Are we moving or are we standing still? Moving. Forwards or backwards? Fast or slow compared to some of the other speeds you see on this graph? So you know what? Let's go right. moving forward slowly. We'll find better, shorter ways to write that in a while, but for now, instead of giving you the, we would say small positive velocity, but we'll use non-physics words right now. Okay? What about right there? Now, I will give you the physics word for this. Begins with the letter R and rhymes with nest. Okay, we say at rest. By the way, for how long am I at rest?
2 seconds.
2 seconds, okay. Oh, in that first one, how fast am I traveling? What's the rise? What's the run? 2? Oh, you already did the, who said that? You? 10 meters? Yeah, you know what? I can say 20 over 2 traveling. Now I can be more specific. So instead of writing moving forward slowly, it's less writing for me to write 10 meters per second. Let's actually write the velocity. And we can just add positive or negative to show backwards or forwards. So here, what's the velocity? What's the rise? Careful, don't say 100 because it's not. Huh? 80, right? Because we started with 20 from here to here. So 80 over, what's the run? In your head, 80 over 2. How fast are we traveling here? Is that fast, Mr. Dueck? It's about 80 miles an hour, so about 135 kilometers per hour. How fast are we traveling here? Oh, you know what? Let's put V equals. Let's. Oh, I can even actually, because it's a velocity, I can put the vector bar over it. Right. What's the first thing that I would write before I did anything else? What do you notice about line CD directionally? Let's do that so we don't forget, because that's a classic one. What's the rise? Starting at 100, ending at 60. What's the rise? Negative, which I got already as a number, 40. Over. What's the run? Negative 20 meters per second. About 40 miles an hour. About 60, 65 kilometers per hour, give or take. A little faster than that. Negative. Negative what? 20 over 2, negative 10 meters per second. A little more notation. If I really wanted to be organized, because I've called this V and V and V, if I really want it to be organized, minimal amount of writing, maximum amount of organization. Jordan, what letter is that right there? What letter is that right there? You know what? I could put a little subscript, BC, and I would call this velocity CD, and I would call this velocity DE. It's 2 letters, but that way I can tell you exactly what I'm talking about very, very clearly, and you know which line to go look at. We'll use subscripts quite a bit to show the difference between one section and another. So that's something you just want to get used to, and we'll do lots of that. You will get used to it. Okay. Looks like this person starts out going forwards slowly, stops for a couple of seconds, maybe waiting for a car to go through a 4-way stop. Now they're on the freeway. Now they've turned around somehow. They're heading back on an on-ramp. I don't know. I can make up some scenario, but I can kind of see what's going on here. Let's answer some of the questions. Find the average speed over each interval. Oh, we did. I knew I was kind of going, I thought I left room for that somewhere. See above. I think in the homework I give you a graph and I say find the average speed. You can do the work right here instead of doing it on the graph like I just did, but that let me keep it all on the same screen. B. What's the average velocity for the entire trip? Well, here's what we've said. We said velocity is displacement over time. What's my displacement? Where was I when I started? What was my position? 0. What was my position when I finished? I don't care what happened in between. All displacement cares about is your change in position. It cares about initial. It cares about final. What was my final position? 40? So my displacement is 40. Time, how many seconds? 10. My average velocity, I can do 40 divided by 10 in my head, is 4 meters per second. What was my average speed? Well, speed, which is v without a vector symbol, is distance, which is d without a vector symbol, over time. Distance asks, how many steps did you take when we had Alexa walking back and forth the other day? Or distance would be, if I look at the graph, how far do I travel going forwards? I start at 0. I end up here. How far have I traveled? 100. Then I keep traveling, and I end up here. How much further do I travel? I don't care that it's backwards. What's the distance that I travel from here to here? 60, right? From 100, and I end at 40, so 60 more. So the distance is going to be 100. Let's write this in our notes, plus 60. In your homework, if you do that in your head, I don't have a problem with that, but I want you to see where the numbers came from. Over how much time? Still 10 seconds. What's my average speed? 100 plus 60, 160. Divided by 10. Hello. 16. Okay. See the difference? Which one's right? Depends what question you're wanting to ask or what you want to use it for. Usually we use velocity, but sometimes we want speed. Certainly if you were trying to figure out how much gasoline you'd need, you'd want your average speed times how long, and you would use that to figure out how much gasoline you burned. Sure. Next page. What's the slope of a distance or position or displacement versus time graph? The velocity. But we need to talk a bit more now about types of slopes. There's an average slope and there is a instantaneous slope. See, what? Oh, patience. As the slope of a displacement time graph is equal to velocity, different slopes indicate different velocities. So, if I gave you this with no numbers, can you tell me when I'm stopped? Which one? What section? Section 3. Can you tell me when I'm going the fastest forward? Section 2. Can you tell me when I'm going the fastest backwards? Section 4. When am I going the fastest? Now that could be 2 or 4 because I didn't give you a direction. Which one is steeper, 2 or 4? I heard someone say 4, and I think 2 is steeper, yeah? I'll make it fairly clear like this. In other words, I won't give you, Oscar, something like that unless I also give you numbers so you can clearly calculate it. But if it's just a freehand graph, it'll be pretty obvious what's steeper and what's shallower. So, positive slope, 0 slope, negative slope. What if it's not a straight line? See, here's what this is really saying. Look up. This is saying you traveled at this speed for a little while, forward, and then boom, instantly you changed and traveled to this speed. That's what that little jerky corner right there means. You instantly sped up, and then instantly you slowed down. Cars don't travel that way. You speed up smoothly. You slow down smoothly. Unless, honestly, that's a car accident, maybe. That could be a head-on collision. But in real life, cars don't travel that way. They travel with curves. Kind of like this here. Here's a much more realistic curve. Instantaneous velocity. Now, I have to pause here. What I'm teaching you right now is terrible. There is a way to find the instantaneous velocity of a curve. In fact, it's why Isaac Newton invented calculus. And you can use calculus to do it. What I'm having to give you right now is a lame workaround. It's an approximation workaround. But how many of you are in calculus? So yeah, so you are? Cool. You are? You're doing calculus? Some of you are. Right now? Not pre-calc. Calculus. Not in calculus. I didn't say pre-calc. Calculus. In other words, if I say to you, what's a limit? You guys don't know what limits are yet, right? You don't know the slope of the tangent line. Okay, by the way, Isaac Newton, the reason he invented calculus was he wanted to answer this, he wanted this question. I want to find the slope of a curve. And he said, I think I can see it visually, I want to get it mathematically. So read along with me, it says this. We want to find the velocity at time 4. So here's time 4, everybody put a dot right there. Look at the slope that goes through that red dot. First of all, can you tell me, are we traveling forwards or backwards at time 4? What do you think? Backwards. Okay, I get that much. I can get a direction. In fact, I would argue, I think the slope, the instantaneous slope, is probably about like that. Not like that. Not like this. About like that. And what Newton found was a way to get that exactly to as many decimal places as you want with calculus. We don't have calculus, so if I want to find the instantaneous slope, we draw what we call a tangent line. What's a tangent line? If you lay I'll show you here, if you lay your ruler down, that's a tangent line. It should go through the dot. Mine's got a bit of a gap. And it should be approximately the same slope right at that dot. I'm going to erase that for a second. I'll show you another one. Suppose I had wanted to find the slope right at time 6 seconds. The tangent line, the slope would look something like, about like that, I think. Definitely not like that. Definitely not like that. Those would be bad. And then what I would do is I would find the rise over run of this on the graph paper, and that's the approximate slope instantaneously at that location. The slope of the tangent lines. Let me bring back my, I didn't really do a good one for 4. I think 4, that's a little better. And yeah, my ruler's got some gouges in it, live with it, it's not quite a straight line. So, a tangent line just touches the graph line, and it has the same slope as the line at that point. So, for me, I can now tell you an approximation to the slope. Yours might be a bit different, and so for these answers, I take a fairly wide range of answers. But for me, my slope is, well, negative, I know that. I'm 7 high right here. I'm 2 high right here. My slope is 5 over 4. My slope is negative 1.25 meters per second. I would probably take anything between negative 1.1 and negative 1.4. And yours might be, mine conveniently, I had some nice points that I could use. I don't know if on your tangent line slope, if you can use that or not. But mine kind of looked like it went through there. That is how, without calculus, you can approximate the slope of a curve at any point. You use its tangent line. Put a dot at the point, line up your ruler approximately with the slope right there, extend the line, and go rise over run from your tangent line. So the velocity at time 4 is the slope of the graph at that point. I think at time 4, this is traveling approximately negative 1.25 meters per second-ish, sort of, kind of, approximately. So, next page. By the way, I didn't check. Negative 4 divided by 5 is negative 1.25, right? I'm doing math in my head. We can use this approach to approximate the curve, the slope of a curve, in order to find the instantaneous velocities. Here's a graph I gave you. This is a much more realistic graph. It looks like this person started out going forwards. Are they speeding up or slowing down at the beginning? How can you tell? Because the slope is getting bigger. Now look, right around here, the slope starts getting smaller. Right around here is where they're tapping the brakes. They're slowing down, slowing down, slowing down, slowing down, slowing down, slowing down. How fast are they going right there for a split second? What would the slope of the tangent line be right there, do you think? 0. They stopped. Oh, they threw it into reverse. Now they're going backwards. And speeding up, going backwards, speeding up, going backwards. See right here where it starts getting less steep? Slowing down. Still going backwards. Slowing down. How fast are they traveling right there, do you think? 0. Stopped for a split second. Threw it back into drive and went forward. Lots of information I can get from a curve. I have to parse it. I have to think about it. So, this is, oh, the word distance got chopped off, so you can add that, please. I'll remember to fix that on the weekend, too. And this time I went in kilometers, and on time I think it's hours. So now we're talking freeway speed, kilometers per hour, which we can also do our units in just fine. So you ready? It says, find the instantaneous velocity for every 30-minute interval on the graph above. And in other words, find the instantaneous velocity for every dot. You know what? Let's be clever. Let's call this dot A. How about B, C, D, E, F, G, H, I, and J. Wait a minute, Mr. Dueck. It said find it for every 30-minute interval. You know what? I guess really I'm only going to do every 30 minutes. 30 minutes is how many hours? Half an hour? I guess I'm only going to do it here, 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 and here. So I'm only going to do B, D, F, H, O, and J. Let's try B together, and then I'm going to let you try the rest of them on your own while I do them up here. Let's see if we end up with the same spot. So B, lay down your ruler approximately equal to the slope. I'm going to lay mine, and then draw the line fairly long so you have some points to work with. So for me, I'm going to kind of go, kind of like that. Is that about what you guys are getting, give or take a little bit? Yeah? No? Kind of? Now, again, John, I would also accept, see, this is why Newton wanted calculus, because it's equally possible I would have no problem if you laid the line down like that, which gives you a totally different slope. But that still kind of looks right. Or if you're a little bit steeper than me, it gives you a totally different slope, but it still kind of looks right. This is why Newton wanted, I want to get calculus. Okay. Why do you draw it nice and long? Because you want to be able to find some points that it goes through so you can go rise over run. And the longer you draw it, the more likely it is that it goes through some nice points. So my line looks like it goes right through there if I extend it. And I guess right through there. It goes through point B. So for me, this is how I'll write this, velocity at B, that's why I labeled these with letters. For me, my rise is 1, 2, well, let's see, 25. What's halfway between 25 and 30? What's halfway between 25 and 30? Exactly. Okay, so mine is 27.5 here and 10 here. My rise is 17.5. Sorry, I can't give you nice numbers all the time. Welcome to the real world data. Over. And my run is 1, 2, 3, 4 squares. What's each square worth horizontally? What's each square worth horizontally? How many squares make up an hour? Count. I don't think 4. 8, right? So each square is 1/8 of an hour. What's 1/8 as a decimal? Someone, please. No, as a decimal. Thank you, Captain Obvious. Yes, I know 1/8 is 1/8. 0.125. So for me, my run is 4 of those. My run is 4 times 0.125. There's other ways. I mean, I also know 4 squares is half an hour. I think it's going to be half an hour. But if you get something yucky, Spencer, looks like horizontally. You see how I figured that out? We said, hey, 1 hour is 8 squares, so each square is 1/8 of an hour, but I made it a decimal, so I can count the number of squares.
Yeah.
With me? Times by 0.125. Okay, so for me, and yours might be different, but it'll be close. I get 17.5 divided by bracket 4 times 0.125. I think I can do this in my head. Prediction, the answer is going to be 35, I think. No, that's wrong, Mr. Dueck. Subtract the 3, carry the... Yeah, 35. Is it? Yeah, booyah. I can do math in my head, even when there's decimals and fractions. Okay, sorry. 35, what? What are the units? What are the units on the y-axis? Kilometers. What are the units on the x-axis? Kilometers per hour. You see how we did that? So, try finding right now, well, the velocity at d is kind of easy. Because I would argue the velocity at d, I mean, it kind of looks like, if I lay my ruler down, kind of looks like it sort of flattens out right there, right? So I don't even need to do arithmetic. What's the slope at d? What's the 0? Okay. Units, kilometers per hour. So try doing on your own velocity at f, and I'll do it. I'm going to freeze the screen. I'll do it up here. Let's see if we get close to the same answer. And by close, so by the way, for velocity at b, I'd probably take almost anything between 30 and 40 kilometers per hour. Because you're laying your ruler down and, okay. And velocity at h and velocity at j. I'm going to freeze the screen. Click. Try this. You work with your neighbor, partner if you need to. Velocity at f. Okay. Looks about right. Let's find some points that it go. Well, it goes through right there. Ooh, goes through right there. Okay, I can do this. 1, 2, 3, 4, 5, 6, 7 squares. 7 squares. And what's each... By the way, vertically, what's each square worth? I think 2.5, yeah? Is that right? Because every 2 squares is 5, so each square is worth vertically 2.5? So for me, I'm getting run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 squares for me. Stuff that goes through the grid evenly. Don't pick stuff hanging in midair, right? Oh, and it's negative. Oh, holy smokes, mine worked out evenly. That's a fluke. For VF, I got -4, first of all, negative, right? And I got -14 kilometers per hour. Let me double check. I could be wrong. So let me unfreeze my screen. I'll show you what I did here. So here's my line, this long red one. So I used this point because it went through a grid line nicely. And I went, what the midair, 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 midair. Ah! Goes through that one down there, my line. So I said, okay, what's my rise? I went 1, 2, 3, 4, 5, 6, 7 squares. Each square is 2.5. So I went 7 times 2.5 right here. Is that okay so far? Then what's my run? I said, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. Each square is worth 0.125. So I said, okay, there's my run. 7 times 2.5 divided by, and you have to put the top in brackets because there's more than one number on the top, divided by, and you got to put the bottom in brackets because there's more than one number on the bottom. I got 14. Yes? No? Or close to 14? 13 point something? Yes. 12 points? Yeah. 16 point something? Yeah. 35? No. Sorry. Oh, and negative. Did I hand up? Nope. Is that okay, Jordan?
Yeah.
You see where you zigged?
Yes,
I'm going to guess counting or timesing, right? Okay. I'll leave the screen on. I'll do velocity h, I guess. I'm going to erase this because it clutters up the graph. Right there. Sheesh. That's a tough one because there's a bump right before, I don't know, before it. Kinda. Sorta. I don't know. This one I'd probably take a wide range of values. I'm going to pretend it looks about like that, maybe. Could be shallow. You know what? I think I'm a little steep. Ay, 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 ay. Sir Isaac Newton, where are you when I need you? How about kind of like that, maybe? That looks better. All right. Oh, hey, and nicely it goes right through there. Does it go through there? You know what? I think it goes right through there. Okay, I can do this. What's my rise? 1, 2, 3, 4, 5, 6, 7 squares. Okay. First of all, it's negative, downhill. 7 squares times 2.5 divided by, what's my run? 1, 2, 3, 4, 5, 6 squares. 6 squares times 0.125. This would be much easier if we were going up by ones, but suck it up. Sometimes the scale isn't going to be by ones. Negative 7 times 2.5 divided by bracket 6 times 0.125. I'm getting a slope for h of around-ish. Negative 23.3333. I'd probably take almost anything between negative 18 and negative 28-ish or something like that, I think. Am I right? Anybody? Am I wrong? I could be wrong. Sorry?
I got negative 28.
Sure, okay. You got the same answer as me?
Yeah, pretty different numbers.
That's fine. It just means that your slope was identical to mine. Okay? Is that okay? Do we need to do J, or do you guys have the hang of it? Because I have some homework where you got to practice this as well. Okay? Now, yeah?
I got a question. How do you find the back points on the H? The bottom point.
How did I find? Well, first of all, I drew my line. You okay with that?
Yeah.
Then I start at the top. Okay, it went through there. That was a nice fluke. And then I just start sliding down. You can see a tiny gap there. No, no, no. I thought it might go through G, but it looks like it's a bit high, so I figured it went right through there. There was my second point. Okay, I didn't actually use the H, because the H is hanging in midair.
Yeah.
Now, you gave me a good lead-in question, though. Mr. Dueck, what if, don't write this down, just watch. First of all, can I erase this and this, because that really clutters up the diagram. What if I don't go through any nice points? In other words, what if I was doing J, and I drew my line, and you can see I don't go through anything. Do I? I don't think I do. I'm in kind of midair. Maybe that top point might be, but even that, it looks like the very, very top one, there's kind of a gap. As long as you don't twist your ruler, that line there has the same slope, and it goes through way more points. That line there has the same slope, and it goes through way more. You can always slide your ruler along the graph as long as you don't twist it at all. And I guarantee you'll find some points that you can go through. And it's got to be the same slope. It's going to be weird numbers, but it's got to be the same steepness, right? I hardly ever have to use that, because I tried to make sure on your tests that you have clear, easier ones to go through. But in a pinch, I've used that trick before. Let's answer the questions. B says, at what time has this person come to a stop? What times has this person come to a stop? There's 2 times. What 2 times have they come to a stop? 1 hour? And T equals? Point I, right? Which is how far along? 2.5 is right there. Thank you for playing. 2 1/4, 2.2. You're giving us decimals! Yeah, I am, on purpose. So I've talked a lot. I went about 10 minutes longer than I planned, but I wanted to make sure you wrapped your brain around it. I have just 2 practice worksheets, one with nice straight line slopes and one with the instantaneous slopes. Okay?